Hi folks, Mr. Ackerman here. Thanks for watching. Topic of today's video is the work-energy theorem. And before we talk about what exactly the work-energy theorem is, let me just go back a little bit and talk about work, which we introduced in the previous lesson. If you recall, we had a formula for work which said work equals magnitude of the force acting on an object times the magnitude of the displacement that it causes times the cosine of the angle between the force vector and the displacement vector. This is an energy idea, and it kind of says to you that there's energy involved in applying a force and moving an object. A certain amount of energy ought to move an object a certain distance if you apply a certain force. But there's something that we often talk about when we talk about movement that is missing from this formula. And I'd like you to pause the video and try to answer the question, what variable seems to be missing from this analysis of motion, which we often talk about naturally when we're discussing motion? See if you can figure it out. Okay, and you're back. And what is that variable? Well, you might have mentioned several variables, but one of them that I noticed that's missing is the idea of time. In fact, distance over a certain time is speed. When you push something, you often cause it to speed up. That seems to be missing from this formula. And really the bigger question that we want to answer, therefore, is when you do work on an object, what exactly is happening to it beyond just moving it? Well, that's what the work-energy theorem is going to tell us. In a moment, I'm going to derive a formula that's going to tell you when you do work on an object, not just how much does it move, but how fast does it get going? Because really, that's a very important concept in motion. So at this point, just pause the video, have a look at where we are in the unit schedule, as well as what the learning goals and success criteria are, and then click it back on and we'll resume. Okay, and you're back, and here we go. Let's get into the work-energy theorem. First off, what I'd like you to consider is the following scenario. Imagine an object on a horizontal surface, at least that was supposed to be horizontal. Let's try that again. There we go. An object on a horizontal surface, and let's call it a frictionless surface. Suppose you apply a force in the forward direction parallel to the floor. So this will be the force, let's call it the F applied. And suppose as a result of this pushing, the object moves a certain displacement. So there is delta D. Of course, the force being parallel to the floor and the displacement being along the floor, the angle between these two is going to be 0 degrees. I'm doing this so that the cosine theta part of the work formula will just be equal to 1. It'll be easy to deal with. Are there other forces acting here? Sure there are. There is gravity, and there is the normal force. I'll just write those in, Fn and Fg. And remember, to keep things simple, we're going to say no friction right now. And so the question I want you to answer is, how much work is done by all of these forces here? In other words, I want you to calculate not just the work done by the applied force, but also the work done by any force like the normal force and gravity. They are forces. There is displacement here. If they do work, we ought to calculate that. Well, first of all, the applied force, we can use our regular formula. F applied delta D cosine of 0 degrees. The normal, on the other hand, that would be Fn delta D. And now, because the normal is perpendicular to the displacement, we're going to have cosine 90 degrees, which of course, the cosine of 90 is 0. So the normal force does no work. And in fact, same goes with gravity, so I'm not even going to bother writing that in. I'm just going to save some time, and we'll write 0 there as well. All we're left with is the work done by the applied force. And so you might think of this as what's called the total work. And therefore, I'm going to just backtrack a little bit here. And maybe you realized this before, but what I was calculating was actually the total work. And so I'm just going to abbreviate that TOT. The total work done in this case happened to be only by the applied force. And just to keep things a little bit easier and quicker, please allow me to write the magnitude of this force vector just like this, with no vector symbol and no absolute value symbol. The magnitude of displacement like this, cosine of 0, that's equal to 1. So here's the total work done. Now, let's go back and analyze this in a little bit more detail. Because the normal and gravity would be equal to one another in this situation, the applied force is also the net force. Remember, there's no friction in our example here, which means I can also write MA. Furthermore, because this object is only moving in one dimension, I'm just going to call positive the direction to the right, and therefore I can drop these vector hats. Positive will be to the right, negative, if there were any, would be to the left. So what does that mean? Well, I can make things even simpler. The applied force, which is the net force, is MA. Delta D stays in there. Now, we can do even more. M is the mass of the object. I guess I should label that here to be fair. A is acceleration. And what is that? That's V2 minus V1 over delta T. Once again, I don't need the vector symbols here. I already told you positive is to the right, so positive values would represent to the right. Delta D stays in there. Okay, now what? Let's get some more space here. I'm going to bring this delta T over so it's underneath the delta D, and that's going to leave me with M, V2 minus V1 times delta D over delta T. What is delta D over delta T? If you said speed, you're wrong. It's average speed. I know that you think I'm just being picky there, but I'm not, because there's a formula for average speed. Maybe you remember it from grade 11 or from earlier on in this course. Delta D, when we're accelerating, which is the case here, because of course it's a net force, you can write V1 plus V2 divided by 2. That's only if it's the average speed. That's not a formula for speed. It's a formula for average speed. So V1 plus V2 over 2. Now where am I going with this? Well, we're almost done. The 2 I'm going to bring out over here so that we end up with a 1/2 times mass. And now look at this. This is V2 minus V1. This is V1 plus V2. I'm going to let you multiply those out to see that you get V2 squared minus V1 squared. You just expand those brackets. And now what I'm going to do is, you distribute those. Now I'm going to expand this bracket here. So 1/2 m V2 squared minus 1/2 m V1 squared is where I end up. And now you take a look at these formulas. It looks like the final value of something and the initial value of something. What is that something? That something you'll probably remember from grade 11, where you learned that 1/2 mass times speed squared is something defined as kinetic energy. And so now do you see what we've done? We've started with the idea of total work done by all of the different forces that are acting. And we've come to realize that they are equal to 1/2 mv squared, the final value, minus 1/2 mv squared, the initial value. When you've got a final minus an initial, you've got in math or science what's called a change or a delta. So in the end, we have realized, we have derived the idea that the total work done equals the delta, the change in kinetic energy. And that is what we call the work-energy theorem. I like to write it as the WE theorem because I'm lazy. But that is it. And that, by the way, is the fact of the video. I know it seems kind of silly. The fact of the video is the actual topic. Yeah. And I'll tell you why. I'm going to tell you a secret. Look to your left, look to your right. Are you sitting beside someone in your class as you watch this video? Well, one of those two people, to your left or your right, is going to make the following mistake. So don't let it be you. One of those two people is going to forget the word total under here. And he or she is going to forget that you have to add every single force's work done. Every single force does work. You've got to add them all up. That's what the word total means. If you don't add them, you will not get the work-energy theorem. What the people who make a mistake are going to do is they're going to write this. W equals delta EK. And they'll forget to add up all the work by all the different forces. Don't be that person. The fact of the video is that it's the total work that matters, and it causes a change in kinetic energy. It doesn't cause kinetic energy, it causes a change. This is all, maybe it sounds really subtle to you, maybe I'm being picky, but as you're going to see in a moment with a couple of examples, if you leave out the word total and if you leave out the symbol delta, you will run into trouble. Here we go, let's try some examples. First example, this is out of your textbook. The textbook is Physics 12 by Nelson. And this is in section 4.2. There's two question 7s. One of them is just in the general practice. One is at the end of the section. This is the first one. Talk about a delivery person who's pulling on a box, exerting a certain force. But there's friction acting on the box. And so if the box starts from rest, use the work-energy theorem to figure out how fast it's going after it's been dragged a certain distance. So let's start off as we start off every single question in physics. Yes, we draw a diagram. I know it takes time and it helps you to figure stuff out, so it's a good use of time. However, we've got a person pulling. Okay, so not being an artist, not very good at this, but here's a person pulling. And it says that the pulling force is above the horizontal. So I'm going to try to show that with maybe a rope of some sort, which is inclined at an angle above the horizontal. Okay? That angle in there, they tell me, is 35 degrees. Of course, if the person's pulling, I don't know, maybe this is a tension force in a rope. So let's show Ft, or F applied, however you want to look at it. And they tell us that it's 95.6 newtons. Writing things in with the correct symbol, all the angles shown, all the values given. What else? They tell us there's a friction force. Okay, so that acts backward. Maybe I'll give it a different color here. Friction acts against the motion, and that value is given as 75.5 newtons. Am I done? No, I'm not done. There's two other forces acting, which you better include, otherwise you might make a mistake of forgetting total. What are those other forces? If you guessed that they are the gravity force and the normal force, you're correct. And if you're saying, why should I waste my time writing these in? Do I really have to? The answer is, this time it wouldn't have been a big deal if you forgot them, but if you get in the habit of leaving stuff out, the one time you need them for some reason or another, you'll be kind of in a careless, you'll have developed a carelessness that will cost you. So draw them in, and then if you see, hey, these are at 90 degrees to the displacement, they're equal in magnitude, they're both equal to 0 work done, then you can leave them out at that point. But don't assume anything until you've drawn it and seen what's going on. There's a displacement of 0.75 meters, so let's show that over here. Box starts here, goes along to there. Delta D equal to 0.75 meters. And now I think we have a nearly complete diagram. We should put in the mass, 20.8 kilograms. Okay, what do we do now? They ask us to use the work-energy theorem. So we remember, some people are going to write this, W equals EK. Those people are wrong. They're going to get the questions wrong. Don't be that person. Remember the fact of the day. It's not work equals EK. It's total work equals the change in kinetic energy. Let's see what we do. Work is done by any force that acts, or it's potentially done by any force that acts. So look at how many forces are on your free body diagram. There's 4 of them. Therefore, there's potentially work done by 4 different forces. There's friction, there is the normal force, there is gravity, and there is the applied force. At this point, I think it's safe to say the angle between the normal and the displacement, and the angle between gravity and the displacement are 90. Cosine of 90 is 0. Therefore, these guys do no work. You've checked it in your diagram. You're safe to cross them out. But what about friction? That should be the force of friction, delta D, cosine of the angle between them. And the applied force should be F applied, displacement, cosine of the angle between those guys. Now, I know I'm using theta here, and I'm using theta here, but they're not the same theta. This theta is the theta between displacement and friction. I've got displacement to the right. I've got friction to the left. So this value is 180 degrees. Here, displacement's to the right, but the pulling force, the applied force, is at 35 degrees to that. So be very careful. This is a 35-degree angle. What is all of this equal to? When you add all of this up, it's supposed to be equal to delta Ek. What's delta Ek? Delta anything is final value minus initial value. Oops, there we go. What do we know? The box starts from rest. So the initial kinetic energy is 0, which means here it is safe to just write the final kinetic energy, which is a half of the mass times the final speed squared. Subtract 0, you still have a half mv final squared. I'm going to leave you at this point to finish this one off on your own. Notice that you're going to get a negative number in here because the cos of 180 is negative 1. Here you're going to get a positive number because the cos of 35 is a positive number. That means that when you sub in these numbers, will you get 0, will you get positive, will you get negative? Well, let's take a look at this. The friction force is 75.5 newtons. Displacement's 0.75 meters. The applied force here is 95.6 newtons. Displacement is the same 0.75 meters. And the cosine of 35 degrees, that's around, I think, about 0.8. So here you're going to have a negative number. Here you're going to have a positive number. If these guys add exactly to 0, then I guess the final speed will be 0. There will have been no change in kinetic energy. If this value is more negative than this one is positive, then overall we will have a negative. Can you get a negative out of this? A half is positive, m is positive, any speed squared will be positive. So I guess right away you know if you get a negative number in total on this left side, you've made a mistake. That tells us that probably, while this number will be negative, this number will be more positive. So you get an overall positive number, and therefore the final speed should be higher than 0, which means the box sped up. That's what the work-energy theorem is telling us. It's telling us that the total work done was positive, and therefore the change in kinetic energy was positive. The box sped up from 0. Try this one. Check that you get the right answer by checking the answers in the book. And if you have trouble, you can send me an email or you can ask me in class. All right, we're going to move on. I'm going to show you another one that gets a little bit trickier. This is the other question 7 in the same textbook, Physics 12 by Nelson, and it's the 7 in the section review at the end of this section. You've got a skier going down a hill that's inclined at a certain angle. I'm going to start drawing. There we go. Here is our skier. Okay, the angle of the hill is 23 degrees, and the mass of the skier is 61 kilograms. I'm using the correct symbols, units, and I'm labeling everything. There is friction. Okay, that acts backward, and I'm going to draw it in right here. Force of friction, which is 72 newtons. And they tell me that the skier has a certain speed near the top of the hill, so I'm going to call that a V1 of 3.5 meters per second. And they ask me, if the skier goes 62 meters down the hill, what is the speed when he gets to the bottom? So what is V2 equal to, given that the displacement here is 62 meters? Well, first of all, I'm not done. I've only shown one force, and you know from your studies of inclined planes there are more forces acting on the skier. For example, there's definitely gravity, so we could draw that straight down. And we could label it Fg. We could even say that's mg. That's 61 times 9.8, which, if I take my calculator here, 61 times 9.8, going to be around 600. It is. It's 597.8 newtons. What other force or forces are acting here? There is a normal force. Unfortunately, I didn't leave myself much room to draw it there, but I'm going to try to anyway. Maybe I'll just do this so that it's easy to see. I'm not suggesting the normal force would be this large. However, I want to make it clear that there is another force acting. Do you remember how to do these questions? You have to place yourself into a slightly different perspective here. We want down the hill, the direction of motion, to be the positive x direction, and we want perpendicular to that to be the y direction. So this is going to be the positive y. This is the positive x. And the skier, of course, is going in this way, which I labeled as displacement. I could just show you that maybe like this. Okay? That's not a force, that's a displacement. Now, let's go back and use the same methodology that we used in the previous question. The work-energy theorem tells us work equals EK? No. The people who like to get sloppy and make mistakes are going to write this. You aren't. You're going to write what the work-energy theorem says. W total equals delta EK. Does it matter? Yes, very much, and you're about to see why. Total work means all the work done by all the forces involved. So let's take a look. I see one force, two forces, three forces. Displacement is not a force. So that means I'm going to put work done by the normal force, work done by the friction force, work done by gravity. What does delta mean? It means final minus initial. So EK final minus EK initial. Now, true or false? The normal force does no work. Well, let's look at the angle. The displacement's down the hill. The normal force, by definition, is perpendicular to the hill, so the normal force here does zero work, and that is because of the 90 degrees between it and the displacement. What about friction? Friction acts backward. The skier goes forward. That's got 180 degrees in there. So this one will not be zero. We have 0 plus force of friction, displacement, cosine theta. Want to know where a lot of people go wrong here? They're not paying attention to what this theta means, and they automatically, without thinking, say, oh yeah, that's 23 degrees. They think of the angle of the hill. But remember, the theta in the work formula is the angle between this vector and that vector. So don't rush to judgment and just sub in the first angle that comes to mind. The angle here is actually 180 degrees. So what do we have so far? The normal force gave us the 0. Here we have a force of friction, 72 newtons. We've got a displacement of 62 meters. And the angle between these two vectors is 180 degrees. Let's move on. Gravity. Does gravity do work? Well, what's the angle between gravity and the displacement? Let's see. Here's a right angle in here. That's 23 degrees. So the angle between gravity and the displacement would be 180 minus 90 for this, minus 23, leaving me whatever's left in the triangle. That looks like 57 degrees. This angle in here is 57, and it is the angle between gravity and the displacement. So what I'm going to put in here for work done by gravity is force of gravity, delta D, cosine of theta. Once again, not the angle of inclination of the hill. That's the knee-jerk reaction to putting in theta. The rule is the angle between the force and the displacement, which we just saw was 57. So what is Fg? Fg, of course, is mg, which we already calculated, by the way. So maybe I'll just write that in, 597.8. What's the displacement? Same, 62 meters. Cosine of 57 degrees. All of this is supposed to be equal to Ek final, I've run out of room here, minus Ek initial. So all of this is equal to Ek final minus Ek initial. What is Ek final minus Ek initial? It's a half mv final squared minus a half mv initial squared. They give you the mass, we've got that. They give you the initial speed, so we've got that. So go and solve for this. You've got everything else. And therefore, I'm going to leave you at this point because that is enough. You can do the calculation on your own. What I do want to point out is that if you are one of those people, and I hope you're not, but if you're one of those people who doesn't pay attention to symbols like this, then you'll never know that it's final minus initial, right? Which means you'll never know to subtract these two values, which means you'll end up with the wrong answer. The work-energy theorem, folks, a lot of people butcher it, but there's no need to. It tells you that the total work done by all the forces equals the change in kinetic energy. It's the fact of the day. Thanks for watching, and I'll see you in class.